Yo, what's up, guys? Welcome back. Episode 133 today. Yeah, sorry, I forgot to post yesterday's video. I just made dinner and was tired and kind of fell asleep, so I forgot to upload it. But I just uploaded it, so we're gonna record today's video though, which is, I believe, episode 133. We got an EV today. 132, we did Ditto yesterday, yeah, so 133 today. Let's take a look at the EV sound. Oh, that's crazy. EV, 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 EV. That's our sound. Drop us some problems. Check out our problem of the day. You got candy. It's a hard problem. Might take a look. There are n children standing in a line. Each line is assigned a rating value given to the integer array ratings. You're giving candies to these children subjected to the following requirements. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. There are n children standing in a line. Each child is assigned a rating value given in the integer array ratings. You are giving candies to these children subjected to the following requirements. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. I don't really understand. These are the ratings of our candies. It's a greedy problem. Okay, so these are n children, right? The size of this is n. So 0, 1, we have 3 children. Each child is assigned a rating value given in the integer array ratings. Okay, so we have 1, 0, 2. You're giving candies to these children subjected to the following requirements. The first child gets 2. So my initial intuition is I feel like I don't understand really the pattern, the greedy pattern that we're looking for. Road problem 0, we have 1. Might have to watch a video on this one, not gonna lie. Hopefully Leetcode has a video. He does.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem candy. We're given an array of n children, and for each child we have their rating in a ratings array. The rules are pretty simple, even though they're a bit poorly worded in the problem statement, but for every single child, we want to give them at least one candy. So I guess that's like a default that we can have. So in this case, we have 3 children. We start with an array of 1, 1, 1, one candy for each child. But there's also a second rule here, and this is the part that's poorly worded, but any child that has a rating higher than its neighbors, and when we're talking about ratings, we're talking about the ratings array. This array is a second array. I guess you could say it's the candy array. But a child like this one, which has a rating of 2, clearly has a rating higher than its neighbor. So we don't necessarily know how much candy this child is going to receive or how much candy this child is going to receive either. But we know for sure this guy is going to have more candy because they have a higher rating. Similarly, this child has a higher rating than its neighbor. It doesn't even have a left neighbor, and this one didn't even have a right neighbor, but it does have more or a higher rating than the middle guy. So this one is also going to get more candy than the middle person. Now, the middle person is smaller than both of its neighbors. So we don't know how much candy they're going to have, but we don't need to give them extra candy. And in this problem, we're trying to actually minimize the total number of candy we give to the children while still following these rules. And then it becomes pretty simple because, of course, the middle child is going to have the minimum number of candy, which is always going to be 1. The left child is going to have the minimum number of candy that we can give them, and we can't give them a candy of 1 because they have a higher rating than their right neighbor, so we have to give them a candy of 2. We could give them more, like 3 or 4, but why do that when we're trying to minimize the candy that we hand out? Same thing for the right child here. We give them a candy of 2, so 2 plus 1 plus 2 is going to be 5. That's going to be the result for this example. The second example is pretty similar, but we run into an interesting edge case. What happens if the candies are actually equal? Well, the middle child does not have more candy than the right child, but it does have more candy than the left child. So we don't know how much candy they're going to get, but we know for sure this child is going to have more candy than the left child. And we know that the left child is probably going to have candy of 1 because we're trying to minimize it. Therefore, the middle child is going to get candy of 2. What about the right child? It has the same candy as its left neighbor. Should we give it 2 candies or can we give it 1 candy? Well, in this problem, we can actually give it 1 candy because while it's equal to the left neighbor, it's not greater than the left neighbor. The rating is not greater than the left neighbor. So we don't have to give them extra candy. Now, if this was a 3, we'd probably have to give this guy a candy of 3 because its rating is higher than the left neighbor. Once you understand the rules, the problem isn't crazy hard, but there is some intuition that we need to pick up, which I'll try to explain. First, quickly, just to better understand the problem, assume we had a array like this. Like these are the ratings, 2, 2, 2, 2. Basically, they're all equal. What would be the candy we give each child in this case? Well, it's easy. We just give them 1, 1, 1. Because none of them have a higher rating than their neighbors. Now, what if we make it a bit more interesting? What if it's in increasing order, 2, 3, 4, 5? How do we know how much candy to give this person? Well, we start at the left because it's a natural spot to start, but notice about the left position, it doesn't have a left neighbor, so that's good, and it does have a right neighbor. So the first thing to probably try here is to just take this guy and compare it with the right neighbor. Well, its rating is less, so that's fine. We can keep this guy with a candy of 1, the minimum amount. Now we look here. Well, let's first compare with the left. It's clearly greater than the left. So while the default value would have been a 1, we know for sure we have to have this value, 1 plus 1. So at the minimum, this person needs at least 2 candy. Well, now let's look at the right person here. Well, 3 is not greater than 4. So this rating is probably good. Now, looking at 4, it's greater than its left neighbor, but not greater than its right neighbor. So at the minimum, it's going to need 2 plus 1, 3 candies. Same for this guy, it's going to need 3 plus 1 candies, so 4 candies. This is not greater than its right neighbor. This one doesn't even have a right neighbor, but it does have a left neighbor, and it's greater than the left neighbor, so it needs more candy. Now, it seems like we can solve this problem in one pass, but this was a very particular case where the values, the ratings, are in increasing order. In the opposite case, what if the values are in decreasing order? 5, 4, 3, 2. Well, and let's try again going left to right. We know we could actually go in reverse order because then the values would be in the same order as this. And we know that this approach did work. So theoretically, doing this in reverse order should work. But what happens if we try it from left to right? Well, here we see 5 is greater than its right neighbor. So we know for sure this guy needs more candy than this guy, but we don't even know how much candy is this one going to get anyway. Like, let's just assume 1. Like, that's the default value for all of these, right? Let's assume 1. Okay, well, we know this guy's going to get more than this. So, okay, I guess I'll put a 2 over here. But I'm really not sure because now when we move to the next position, we're at 4, we look and see, okay, well, I'm not greater than the left neighbor, but I am greater than the right neighbor, 3. So at the very least, I need more than 1 candy. I need to have at least 2 candy here, but now you kind of see the problem, right? We have 2 candies here and 2 candies here. That's not going to work. This one should have more than this guy. So what do? Like, one theoretical approach is, okay, we looked at this element. Now when we look at the second element, how about we have to come back and revisit this one? And then when we look at the third element, we have to revisit all of these. Well, that's going to be nested loops, and that's going to be n squared. That's not the best approach. There is a better way. And the hint is that with this approach, we're going left to right. With this approach, it would probably be better to go right to left. And the general case where we have values in not increasing or decreasing order, but they're like random, like now we have a 3, now we have a 5, now we have a 6, now back to 2. In the general case, like this example, what we're going to do is initialize all of the values with 1. So we're going to start at the beginning, but the approach is going to be this. We're going to first go left to right. When we do go left to right, as we learned with this example, it's pretty easy when we just compare every value with the value to the left of it. Because when we are doing that, we've already gone through all the other values to the left. So we can be pretty sure about the value that we place here, about the quantity of candies. But we don't necessarily know, like looking at the right neighbor, for example, from 4, we know 4 is greater than 3. So this should have more candy than this, but we don't even know how much candy this should have yet until we've gone through the entire array. So basically, in the first pass, we're ensuring that any particular value will have more candy than its left neighbor if the rating is greater than the left rating. And then we're going to do the same thing going from right to left. We're going to ensure that this guy has more candy than it had. With this, let's do back to 2. In the general case, like this example, what we're going to do is initialize all of the values with 1. So we're going to start at the beginning, but the approach is going to be this. We're going to first go left to right. When we do go left to right, as we learned with this example, it's pretty easy when we just compare every value with the value to the left of it. Because when we are doing that, we've already gone through all the other values to the left. So we can be pretty sure about the value that we place here, about the quantity of candies. But we don't necessarily know, like looking at the right neighbor, for example, from 4, we know 4 is greater than 3. So this should have more candy than this. But we don't even know how much candy this should have yet until we've gone through the entire array. So basically, in the first pass, we're ensuring that any particular value will have more candy than its left neighbor if the rating is greater than the left rating. And then we're going to do the same thing going from right to left. We're going to ensure that this guy has more candy than its right neighbor if the rating is greater than the right neighbor. And I'll quickly go through this. Starting at 5, doesn't have a left neighbor. 4 has a left neighbor, but it's less than the left neighbor. This is also less than the left neighbor. This is greater than the left neighbor. So at the very least, this should have a candy of 2. This is also greater than the left neighbor. At the very least, it should have a candy of 3. This is not greater than the left neighbor. We can leave it with a candy of 1. So this is not the result quite yet, but this guarantees that anyone that's greater than the left neighbor will have more candy. Now we just have to make that same thing true for everyone with a right neighbor. So now we're going to go in reverse order. This one does not have a right neighbor. We leave it with a rating of 1. This one has a right neighbor, and it's greater than the right neighbor. So what do? Should we add to this? No, because it's already a greater candy. It's already more candy than the right neighbor, so we're good. We don't have to do anything here. Looking at this guy, 5 is not greater than 6. Don't need to do anything here. 3 is not greater than 5. Don't do anything. 4 is greater than 3, so we need to make sure that this has more candy than the right neighbor. They're both equal right now, so let's increment this to 2. And here, lastly, 5 is greater than 4. We need more candy than 2, so we're going to put a 3 here. Now, you take all these values, total them up, and return them. I think it's something like 12. And clearly, we were able to do this in 1, 2 passes. And then if you want to sum up all these numbers, I guess that could be another pass. But overall, the time complexity is going to be big O of n, no extra memory needed. Now let's code it up. Okay, so
times the length of ratings. Let's print out res. Okay. In range, length, ratings. If so, we check. Oh yeah, could you go to the door? Yeah, I'll come out in a second to talk to you. 1 second. If ratings high. Ow. Jeez. We have to check if it's inbounds first, right? So we'd have to do inbounds. Okay, we'd have to do, well, if I is greater, if 0 is equal to I, but is less than or equal to the length of ratings. And rating I minus 1. What are we checking? If it's
element, so candies here and 2 candies here, that's not going to work. This one should have more than this guy. So what do? Like, one theoretical approach can be, there is a better approach. It would values in not increasing or decreasing order. In the general case, the values with this, we're going to first go left to right. When we do, just compare every value with the value to the left of it, because when we are doing that, we've already gone through all the other values to the left. So we can be pretty sure about the value that we place here, about the quantity of candies, but we don't necessarily know, like looking at the right neighbor, for example, from 4, we know 4 is greater than 3. So this should have more candy than this, but we don't even know how much candy this should have yet until we've gone through the entire array. So basically, in the first pass, we're ensuring that any particular value will have more candy than its left neighbor if the rating is greater than the left rating. And then we're going to do the same thing going from right to left. We're going to ensure that this guy has more candy than its right neighbor if the rating is greater than the right neighbor. And I'll quickly go through this. Starting at 5, doesn't have a left neighbor. 4 has a left neighbor, but it's less than the left neighbor. This is also less than the left neighbor. This is greater than the left neighbor. So at the
Okay, so if ratings I is greater than ratings I minus 1, then
very least, this should have a candy of 2. This is also greater than the left neighbor. At the very least, it should have a candy of 3.
ratings I is equal to ratings I minus 1 plus 1. Okay.
3. This is not greater than the left neighbor. We can leave it with a candy of 1. So this is not the result quite yet, but this guarantees that anyone that's greater than the left neighbor will have more candy. Now we just have to make that same thing true for everyone with a right neighbor. So now we're going to go in reverse order. This one does not have a right neighbor.
Okay, so now we go in reverse. So we would do for I in range, length, ratings. To go in reverse, I think we go minus 1, minus 1. Okay, then we check, well, if ratings first we have to check if it's in bounds. If 0 is less than or equal to I, but it's less than or equal to length, ratings. I don't think we'd have to check I, because I is always going to be in bounds. We'd probably have to check I think here we'd have to check I plus 1, right? Because if I plus 1 is out of bounds, then we can just continue, right? Otherwise here we'd have to check if I minus 1, or I guess is it minus 1 in terms of going in reverse? Ratings and ratings I is greater than ratings I plus 1. We do ratings I is equal to ratings I plus 1 plus 1. Else we would just continue, right? Then we would return the sum of count. So we would return the sum of res. But I don't know. This is looping in reverse properly. Is this looping in reverse? Take a look at his code.
Easier just to take the sum of the array.
Okay, so we were pretty close. I just know I did this loop wrong. Oh, he starts from 1, so he can avoid the out of bounds check. Let's do that. That's actually really smart. thing to do. We start at 1. That means we can get rid of this boundary check. Okay. We can get rid of this. Here we'd have to start from -2. -1 of ratings. We can get rid of this. Ratings I is greater than I plus 1. Array I, ratings I is equal to ratings I minus 1 plus 1. Array I is equal to max of array I. Let's get rid of this. Let's see what it gives us here. I guess this is all meant to be res. My bad. Res. Yeah. But I believe we're going to get an error here. We need the max here. Okay. Let's see what he says when he does the
and
math.
whatever we were going to place here. So going back to the code, actually what I'm going to put here, we're going to do that to it too. Actually, no, because, and this is a very easy spot to make a bug. I'll quickly go back to the drawing explanation. Remember here, when we started, we were going left to right. There was already a 3 placed here, and now we're going right to left. We're looking at 6. 6 has a higher rating than its right neighbor 2. So should we take the rating or the number of candy for 2 and add 1 to it and then move it over here? That would be a 2 over here. No, we shouldn't do that, because why would we ever want to make the candy smaller? We never want to do that. This needed 3 candy because its left neighbor has 2 candy. So basically, we're going to always take the maximum of this value and whatever we were going to place here. So going back to the code, actually what I'm going to put here is the max of itself and its the other value we were going to place here. It's right neighbor's candy plus 1. And the reason
So we want the max of itself res I plus 1. That should submit. Nice. That was not too bad of a hard problem. I was expecting something a lot more difficult than that. But I'll be back in a second. I'm going to talk to my roommate for a little bit, and then I will be back. Alright guys, I'm back. Let's jump into a few more problems today. Let's take one more problem out of Leetcode 75. I feel like we should probably take a look at this problem. There's a reason why we probably left this out, but honestly, I'm not sure. Given an array of characters chars, try to compress it using the following algorithm. Begin with an empty string s for each group of consecutive repeating characters in chars. If the group's length is 1, append the character to s. Use only constant extra space. Yeah, so I think we have to use a string, but in range length chars. Let's print chars I. Okay. Let's do our res is equal to this, right? I guess we can make it equal to A. It doesn't really matter, right? So we are fine range there. If char is equal to char's I, if they're the same, we would do so we can do the length is equal to 0. Length plus or equal to 1. And then else we would do length is equal to 1. I guess we can do another if. Check the next, right? Maybe we can check the next value. If char I plus 1 does not equal, or if char does not equal char I plus 1, then we would res.append char res.append the length. Else we'd make the length equal to 1, and then we make the length equal to 1, and then char is equal to char's I, and we would return our res. This is probably wrong. There's no way it's this easy. Is it add? That adds to a string in Python? Add to a string in Python. Res. Is equal to res plus plus char, and then we would do res is equal to res plus length. have to convert this into a, cast this into a string. Oh, whoops. Cast this into a string. Index is out of range. And and 0 is less than or equal to we're comparing to the right every time, so JAWS, then we would just simply, we would append everything, right? Maybe check it to the max. Do. I know it could be anything in JAWS. Out of bound access. Oh shit, we don't need chars. Why are we referencing chars? Okay, we have to check this first. I forgot that. We always have to check the range first. Return the length of res. Chars is equal to res. If not chars, we want to return 0. Okay. That's actually a good idea, making it equal to the first character there. Length is equal to 1. We loop through starting from the one in front of it. Else, if what would we append first? We'd append char, so we do res equal to char. If the length of char is greater than 1, then we do res plus or equal to the length. Sorry, we cast string into the length. Char is equal to char's I. Length is equal to 1. We go through, we'd have to add the final group being res plus or equal to char if length is greater than 1. Res plus or equal to the string of length. Not modifying chars in place, Leetcode requires you that you modify them. I have to do it in place. I thought this only uses constant extra space. Oh, no, yeah. Doesn't it? I mean, we're using a string, I guess. I don't know. That's where it says it. I didn't see that. How would we do this in place? While read is less than chars. If count is greater than 1. That's an interesting way they do this here. They do a write is equal to 0 and a read is equal to 0, right? Go while read is less than the length of chars. Well, read. Char is equal to chars read. Count at 0, right? While read count plus or equal to 1, right? We get outside of it, then we would do, well, if write is equal to char, we do write plus or equal to 1. Then if count is greater than 1, we'd have to go 4-digit in string count. Char's right is equal to digit. Right plus or equal to 1. Then we would return our right. how does it make this smaller? So we keep the right here. We do char's right is equal to char, right? So we make this equal to the char. Then for the next one, we would do, okay, well, if it's greater than 2, let's walk through a test case. Four-digit in string count. Oh, for digit in string count. I thought we were looping up to that number for digit in string count. Okay, so that's if there's multiple digits, if there's multiple numbers. Okay. So like if we had a 12. I understand. Okay. I understand now. Okay, let's finish off with the graph problem. My roommate's cooking up a storm out there. I won't do this one today. Let's take a look at this one again. There are n cities known from 0 to n minus 1 and n minus 1 rows, so there is only one way to travel between two different cities. They are too narrow. Road from city AI to BI. This year there will be a big event in the capital city, 0, and many want to travel to the city. It consists of reorientating some roads such that each city can visit the city 0. Oh, that just changed. So how would we know? Okay. So ECD can visit CD0, return the minimum number of edges changed. It's guaranteed that ECD can reach 0 after a reorder. So really we're just reversing the edges. So the only way I think about solving these problems is with an adjacency list. And I'm thinking if I use an adjacency list, how can I reorder these edges? How are they supposed to get her? I'm trying to think. How did I do it here? Did I use an adjacency list? Curious. So I did BFS here. What did I do here? I did DFS. DFS. So passing edges. For AB is equal to edge graph A dot append B. You can return our graph. Let's create it. Graph is equal to EJ list connections. Let's print our graph. Oh, I can print our graph. because we're not getting all of them. So I think what we have to do is get rid of this. AB is equal to edge. If A not in graph A is equal to this. If B not in graph B is equal to this. Since we have to make it undirected, we have to do both edges. Oh my gosh, I'm appending the wrong one. This needs to be A. That's why. I was like looking at it. I was like, is that right? No. Can create our queue. I think we'd have to do probably q.append our source, which would be 0. Ow, my legs, bro. Opa. Okay, we need a set. So set directed edges. Set. Directed edges, we can do directed edges dot add AB. Okay, that worked. That now we're gonna need a res too, because we need to count the amount of edges, right? Okay, so then we need a res. We need a visited set, apparently. Dot append 0. While queue, we do node dot pop left. Sorry. Node is equal to q dot pop left. And we would check, well, for neighbor in graph node, right? If neighbor not in visited, then we would append it, right? So we would do q dot append neighbor, add it to visited. Here is where we would check. Well, if current neighbor, if current neighbor in visited, sorry, in our directed edges, then we know that this needs to be reversed, so we can count it by 1. Come out here, turn our count. Has no attribute pop left. It's because it needs to be a list. What is going on here? I don't know why why are we getting an attribute error? Attribute pop left. Q. Oh my gosh, I'm not even making it a Q. I'm making it DQ. Jeez, man, what am I doing? From collections, import DQ. Hashable list. Hashable list. Node. Res. And hashable type list. Hashable type list. Why are we getting this error now? Oh. Me too. Something wrong here. We're getting 0. Should be. Something wrong here. Okay. Alright, sounds good. Well, we did that one today, so that's good. Makes sense. Let's just double check what we did here in April. What do we do here? What is needs reversal? Okay, we did it like that. Interesting. Okay. Okay. Well, yeah. Anyway, I appreciate you guys watching, and I'll see you guys tomorrow.